the beautiful northern studios of Way Happy, this is Mr. Meyer coming to you live as we talk about graphs of logarithmic functions. So we have already worked with exponential functions, right? Growth and decay. We have, and there you see them right there, right? Here's a beautiful decay graph. Here is a beautiful growth graph. What are those things we know about those functions, right? They were of the form a to the x power, and we knew things like they had a horizontal asymptote, right, at y equals 0, and both of them actually did, as long as they weren't shifted up or down. And they had some x-intercepts, and they lived continuously above the x-axis or below if, again, they weren't shifted. So now that we've studied logarithms, logarithms are just the inverse of exponentials, which means if you take a graph and you reflect that graph over its y equals x line, that's an inverse. And so if you're an inverse, I should be able to reflect you over that line, and that would make our graph of your inverse function, right? So that's what we're going to do. And so you might notice some things like instead of having an asymptote that's y equals, it'll be x equals. Now, why does that make sense? Because remember, when you find inverses, you switch x and y. So if the asymptote was y equals 0, switch x and y, you get x equals 0. So this is going to be interesting, and that brings up one of our domain restrictions that have always been in effect that we mention here and there, and I'm going to highlight it right here. But this is a very important thing. Logarithms, when you take a log, you can only take the log of positive values. You can't do it for negative values. You can't do it for 0. So anything bigger than 0, you can take the logarithm of, but other than that, you can't. So make sure you pay attention to that. Now, there's that log graph that I was talking about. You can see right there, there's the y equals x line, here's the a equals x graph, and now here's the log graph. It is a reflection. Notice it looks like a reflection over that diagonal line. Especially noticeable in this one over here, right, where you have the growth graph instead of a decay graph, and notice what it looks like. Now, there will be some things that we want to do. We want to make sure that we never take the logarithm of negatives. We want to make sure maybe that we take some values of logarithms that we know, and so I'm going to show you a way to graph them. So here is example 1. Consider the function log base 2 of x minus 1 plus 1. And I want you to find the domain and range. I want you to find asymptotes and stuff like that. So beautiful. If I'm going to do that, the first thing I'm going to do is get myself a set of axes. So here's my axes. And the first thing I like to do is plot some points. I know it says find domain and range and all that stuff, and sketch isn't until part C, but I think that's going to be something I'm going to try. Like, let's go to table of values. We don't want to take logarithms of anything that's going to give us 0 there, or anything that's 0 or smaller. So I can tell you right now that x minus 1 has to be greater than or equal to 0. So x has to be greater than or equal to 1. So there's already some hints, right? Especially hints for domain. In fact, that is your domain, right? You can't do anything that is smaller than 1. Why? Because I can't take the log of a negative number. So just seeing the word log makes me say, hey, make sure that that's positive. So that's kind of nice. I could also give you some values like plug something in. If I plug in x equals 2, now why would I pick 2? Because what would that do? That would give me log base 2 of 1. And do you know log base 2? Yeah, I know there's a plus 1 hanging there, but I'll do that in a minute. Do you know log base 2 of 1? Log base 2 or log base anything of 1, what is that always going to equal? That's always going to equal 0. The exponent you put on 2 to get a 1. Right, is always a 0. So this is going to be 0 plus 1. So one of the points on the graph is going to be the point 2, 1. That's super nice. You've already figured out that x has to be greater than 1, so there's your asymptote, right, that x has to be greater than 1. And I could probably pick another point. What's another 2 that I would know? Maybe log 2 of 4, right? So if I make x a 5, now, why would I pick 5? Oops, sorry, why did I do that? If I make x 5, right, that would be log 2 of 5 minus 1, which I happen to know what log 2 of 4 is, right? So log 2 of 4 is 2 plus 1, which is 3. So if you go all the way out to 5, 3, 4, 5, you'd go up to 3. There would be your next point. Now, again, these are growth and decay graphs. And now that's a good enough hint. I get 2 points. I know what's going on, right? I know that the graph starts at the asymptote and then grows away from it. So it's going to start here, and it's going to shoot through there, and boom, There's your logarithmic graph. So that is the graph of log base 2 x minus 1 plus 1. There's your graph. Beautiful. Now, they said, what else did they say? Oh, find the domain and range. So if I want to answer part A, right? So part A, the domain is domain. I'm going to do an interval notation. So I'm going to say from 1 to infinity. The range, I'm going to say, is all real numbers. Part B, they ask us sketch the find the asymptotes. We did. That's x equals 1. Part C, sketch. We did. So I'll just put C here. And then change this to a D. Part D, find the inverse and explain how to verify your answer. All right, what is the inverse? So if you have y equals log base 2 of x minus 1 plus 1, then the inverse would be x equals log base 2 of y minus 1 plus 1. And then I would say, all right, I don't think I have enough room. Oh, I do have room. Never mind. Then I would do minus 1 on both sides. And we have a logarithmic equation. And how can you get rid of that? Exponential, right? If I make this an exponential and this an exponent, that's legal. And now I have 2 to the x minus 1 equals, those are inverses of each other, so y minus 1. And lo and behold, y equals 2 to the x minus 1 plus 1 is the inverse. And that is what they wanted. All right. Let's try another one before I ask you a question. All right, what about this one? Consider the function. Ooh, just wrote it a different way. No big deal. All right, so if I'm going to go ahead and try this, find the equation of the inverse. Okay, we just did that. So we're going to have, here, I'll do it a little more IBE for you. I'd be like, since f of x equals e to the x minus 3, then f to the negative 1 of x is equal to, now remember, that would be y is equal to e to the x minus 3. So now I got to find out the inverse of it. So, switch by is given by x equals e to the y minus 3. Therefore, now we could go ahead and start solving. I don't know, what do you want to do? Log both sides, natural log. ln of x equals y minus 3. And then add 3. Y is equal to ln of x plus 3. So there it is, the graph that we were looking for. Now in part B, they want me to go ahead and sketch this. Oh, I should have left that in black actually. So in part B, we're going to go ahead and sketch this. So I don't know, what would I do for the first one? Let's do e to the x minus 3. You could use technology at this point, but I'm just going to go ahead and use a graph, right? If I use x is 3, then I get e to the 0, which is 1. So 1, 2, 3 is 1. Probably should use graph paper. What else would be another easy one? Maybe when, I need one more point really. I notice it's growth, and I just wish I really had another growth point. So let's just go ahead and do 4. I don't know if I like that point, but probably could have thought of something better. Which is e to the 1, right? Which is approximately 2.718. So if you go to 4, you're going to go up to 2.718. So you're going to be about right here-ish. Now remember, it has an asymptote at 0 because there was no shift, and then it went like this. Now let's do the other guy, the log. So ln of x plus 3. So x and y, well, there's one logarithm I always know, right, is when x is 1. Doesn't matter what the base is. So ln of 1 is always going to be 0, and 0 plus 3 is 3. So 1, 3 is on the graph. And let's see if I can do another one. I don't know. That's going to be really hard with ln, isn't it? And I guess the other point I could do is e, right? Because ln of e plus 3 would probably be pretty easy to figure out, right? That'd be 1 plus 3 is 4. Now the hard part is graphing e is 2.7 like we just had to do. So 2.7, let's call it about right here, and up to about 4, be right there. And so you could see that this graph would go. Now how did I know it has that kind of straight down line? Because I know it's a logarithm, right? And they are inverses of each other. So there you go. There would be my sketches. Now, I think you can handle domain and range, but domain is all real for the red one and bigger than 0 for the range. And for the y values, for the blue one, the domain is anything bigger than 0 and all real for the y's. Find any asymptotes. You know that this one is right here is x equals 0. This one is y equals 0. The red one, I should have done that in red, right? Y equals 0, just so you don't get confused. And what else could I ask you? Asymptotes. When x is 0, I need a calculator for the red one. So if I wanted to find this asymptote, this x-intercept right here, I would have to figure out when x is 0. That'd be e to the negative 3, I believe. And so I could actually write it like that. I could say the x-intercept is 0 comma e to the negative 3. That would be perfectly okay. For the blue one, we would also do the same thing. We would say, all right, tell me when x is, no, that doesn't have a y-intercept, it has an x-intercept. So I'd have to solve for when does that equal 0. I guess I'd have to get almost the exact same thing, right? Because think about it, you would have 0, let me see, am I in blue? You would have 0 equals ln of x plus 3. You would move the 3 over, and you'd have ln of x, and then you'd Euler numbers both sides, and you'd get x equals e to the negative 3. Holy smokes! So this guy would be e to the negative 3 comma 0. Now, wait a minute, that makes sense if they're reflected over that y equals x line. All right, let me ask you a question, and we will be right back. Hey, nice hard work on that one. All right, now let's go ahead and try to solve some of these. So now, solving could be a little tricky. Like, look at this example. We have a growth graph on this side, and we have a quadratic on this side. So if I kind of think about that, right, I'll do the growth graph in green, and then a quadratic in gray, right? Looks like that. So therefore, I wonder where these two things are equal or where they intersect. Mathematically, pretty hard to do because one side's going to involve logarithms, one side's probably going to involve quadratic formula. So it might just be easier to go into the graphing calculator, which I've already put in. Hit y equals, type d to the x in y1, 2x squared plus x plus 1 in the other. And now I can go ahead and look at the graph. So if I go ahead and graph this, zoom 6 to get a good window if you want. Zoom 6 is your standard window. And if I graph that, I get a nice graph. I kind of wish I could see some more though, right? Like maybe I want my x's to go from -1 to 5, but I want my y's to go a little higher. So I'm going to go -1 to 5 on the x's. And my y's, I don't need to go down so far because I understand the graph, but maybe I want to go up to 20 just to see. And so I'm going to go ahead and hit graph. There's one in there. Ooh, look at that. They look like some weirdness is going on. In fact, I may want to make this window a little taller. Maybe I want to go up to 30 because I feel like they're intersecting again. I think there's 2 points of intersection is what I'm trying to get to. So there's one. There definitely is. There looks like there's one around 0. And there also looks like there's one up there. So how do I find them? Second, calculate, intersect, right? Hit enter for the first graph. It's saying is the first graph equals x. Yep. Is the second graph that? Yep. And where do you think the answer is? To me, it looks like 1, 2, maybe around 3. And I hit 3, and it says, boom, there's one, 3.21. And then if I want to find the other one, second, calculate. I'm going to say, I don't know if I hit intersect that time. Let me try second, calculate, intersect. Is the first one the blue one? Yeah. Is the red one? Yeah. Where do you think your guess is? I think it's around 0. And look, they do intersect at 0. So there is 2 answers there. X equals 0, and the other one was x equals 3.21. So there are my 2 solving solutions using technology. Now the other one, when is it greater? That's kind of a graphing question. So the red line was my parabola. When is the red line? That's what this says over here. When is the e to the x above the parabola? So that's kind of a neat question. So when is the e to the x, the blue line, when is it above the red line? And so the only time I notice the blue line above the red line is when we have, 3.2 to infinity. So I would say from 3.21 to infinity is the only time. Not too bad, right? Well, I have, as I look at my time, 15 seconds. That's not going to be enough. So, let me pause. So in this next one, it's just quick to show you that you can use logs. See all that beautiful work? Logged both sides, divided by 0.7, got my